Hello and welcome to my chemistry video lessons. The topic for this video is the quantum mechanical model for an atom. Humans believed that the Earth was the center of the universe because what we used to see was that the moon revolved around us, and when we looked up at the sky we saw the sun moving around us, we saw the stars moving around us, we saw the planets moving around us. So it was like we were in the center and we were looking at all this motion around us. It was not until much later that science developed and our knowledge of the universe increased, and we realized that it is not us that is in the center of the universe. It's not we around whom, it's not the earth around which the sun is revolving, rather it's the other way around. So as knowledge increases, deeper tiers of reality become visible to us, which are not usually visible at the surface because of our limited knowledge and because of where we are and because of our limitations of our being able to see a thing. The same thing happened in our knowledge of the structure of an atom. The atom was so small that it was impossible to know its structure. And that's the reason why we have been doing these many videos of the study of how the study of the structure of an atom progressed. Now we come to the final stage. The quantum mechanical model actually shows us the deeper tiers of reality of the structure of an atom. We are aware that Max Planck and Albert Einstein, they had established that energy is quantized. And they talked about the electromagnetic radiations having duality. That is, they had wave-particle duality. They were known to be waves, but their particle nature was established. And this wave-particle duality was extended to matter by the scientist called de Broglie. What did he say? That if electromagnetic radiations, which we know to be waves, have particle-like nature, then matter that we know to be particles should have wave-like nature. And therefore matter should also have dual nature. And when he studied, he gave a mathematical value for the wavelength. If matter is particle, then it should have a wavelength. And the value that he gave for the wavelength lambda was, the equation was lambda is equal to h over mv. But then why wasn't this wave nature visible for macroscopic objects? He gave the explanation that the mass is in the denominator and the mass for a macroscopic object is much larger in comparison to the wavelength. And therefore the wavelength is so minuscule, it is so small that it's not visible to us, and hence we can only see the particle-like nature of macroscopic objects and we can't see the wave-like nature. But if you come to subatomic particles like electrons, then the mass is so small that its wave nature becomes very prominent, and therefore it can be observed, although with very strong instruments. Then he said that alright, if electron has both wave-like nature and particle-like nature, then what kind of a wave is an electron? And the explanation given was that an electron is a standing wave. A standing wave is a continuous wave. Now, for example, if you pluck the string of a guitar, it's a standing wave. It just vibrates and it continues to vibrate for a long time. Such a wave is known as a standing wave. But a guitar string is a linear wave. And because the guitar string is tied on two ends and it's a line, it's linear, it's straight. And he said that an electron is not a linear wave, it is a standing wave, but it's a circular wave. The moment you understand that it's a circular wave, quantization becomes evident. The reason for quantization can be understood very easily. If it's a standing wave, then the end of a wave should be the beginning of the first wave. The end of the last wavelength should be the beginning of the first wavelength for the cycle to continue. So from this idea emerged the the Bohr's model of an atom. Let me explain to you how did that happen. For example, if you have just one wavelength, then a wavelength means one full crest and one full trough. And that should come and join. It should complete a cycle, and then the new wave should again begin at the same point. The crest for half the cycle and the trough for half the circle, and again it comes back to the same point. So this should be the energy level n is equal to 1, where there is only one wavelength in the Bohr's model. For n is equal to 2, there should be two wavelengths, and the end of the second wavelength, this is the second one that I've made. There is this is the crest and this is the trough. One wave, this is the crest and this is the trough, and it becomes the beginning, the end of this wave. The second wavelength becomes the beginning of the next cycle. If you had energy levels anywhere between these, this situation would not arise. The end of one wavelength would not be the beginning of the last wavelength, would not be the beginning of the first wavelength, and hence the cycle would be broken. The standing wave would not exist. So this explains the Bohr's model very clearly, and this also explains quantization. Why all energy levels were not possible? Because only integer number of wavelengths were possible in order to make a circular standing wave. Now this was a huge step towards understanding quantization and towards understanding the structure of an atom. Now there were two scientists that we have already studied about. That was Heisenberg. Werner Heisenberg and Erwin Schrödinger, they were working simultaneously to explain the quantization of an atom and to explain the quantum mechanical model of an atom. We know about Heisenberg. He said that he took into consideration both the wave-like and particle-like nature of electrons, and he said that it is impossible to simultaneously tell exactly the position and the momentum of an electron. It is impossible to tell them simultaneously. You can never give an exact position and the exact momentum of an electron simultaneously. And on the other hand, Erwin Schrödinger, he gave a mathematical equation. And in 1926, he gave this mathematical equation, which is now popularly known as the Schrödinger wave equation. The Schrödinger wave equation, and in 1933, he got the Nobel Prize for Physics for this equation that he had given, which became the backbone of the quantum mechanical model of an atom. The equation was h psi is equal to E psi, where h cap is known as the Hamiltonian operator. The Schrödinger wave equation is a complex differential equation, and the solution of this equation is not possible at our level of study. You will study this in higher classes, but let me just tell you what this equation did. What did it have? The h psi was known as the Hamiltonian operator, which was a mathematical operator, and the solution to this equation gave us the values of E and psi. E was the total energy of the system, that is, the energy of an atom would be, the total energy would be the kinetic energy of all the particles, the electrons, the protons, whatever particles are present in the atom, the forces of attraction between the electrons and the nucleus, and the forces of repulsion between different electrons and between the protons present inside the nucleus. So it took all these energies, and the sum of all these energies formed the total energy of the system. So the solution gave us the total energy of the system, and it gave us the values of psi, and psi is known as the wave function. The solution to the Schrödinger wave equation gave us certain numbers which were known as the quantum numbers. It was like, this is where I live. So if you want to know my address, you should know the name of this country where I stay, the name of the city, the name of the street, the name of the lane, and the number of my house in order to know where I am. Now, if you have all this information about the country, the city, the lane, and the house number, the street, lane, house number, you can reach my house. And I am present inside this building. But inside the building, I could be present anywhere. I could be in this room, I could be in the living room, I could be in the bathroom, I could be in the kitchen. So there is a probability of me being anywhere within this house. But this house is my address. So these quantum numbers were the address of an electron. They told you the address of, and this address of an electron in the chemical world or in the scientific world is known as the orbital. The name we give it, I call this my house, but the house of an electron would be an orbital. So the solution of the Schrödinger wave equation gave us the numbers which were the address of an electron, and they led us to an orbital where the electron may be present. So that is how the Schrödinger wave equation was used, and that is how we'll be progressing with the quantum mechanical model of an atom. Now, in the next video, we are going to start off from the Schrödinger wave equation and the quantum numbers, and we will study about quantum mechanics from there. Thank you for watching my video. Please like the video if you found it useful, subscribe to my channel, and please keep returning for more videos in chemistry. Bye-bye.